Hello everyone, welcome to this hands-on session. Today we will construct a cluster expansion model for lithium nickel oxide. Lithium nickel oxide is a prototypical cathode for lithium ion batteries. We will be using a small package to construct our CE model. A small package is a Python based package to construct any CE model. Okay. Cluster expansion, as you know from the lectures, it is a formalism in which we write the energy of any configuration as the linear combination of cluster basis. Okay. What is the cluster basis? Cluster basis represents correlation of site occupations for a cluster. So it represents this correlation of site occupations of any cluster, say a point cluster, this pair cluster, triplet cluster, or any higher order cluster. So what we basically do, we project our DFT energies onto this cluster basis functions. Once we project this DFT energy onto this cluster basis, we find something known as cluster interactions, which are also known as effective cluster interactions. Once we find the effective cluster interactions of any system, then we can use those ECI values or effective cluster interaction values to find the energy of any other configuration. Okay. So let us get started. So in the current model, we will be using this Li-NiO2 system, a prototypical cathode material for the lithium ion batteries, and this CE model allows us to efficiently predict the configurational energy of partially lithiated structure, which are otherwise computationally expensive. So what we will do, the CE will be trained on a relatively small set of DFT relaxed structures with various combinations of, say, lithium vacancy configurations in the lithium sublattice and nickel 3+, nickel 4+ oxidation status in the transition metal sublattice. Okay. So let us first import some necessary libraries. Say import random here, we are importing numpy as np, cluster subspaces here, structure wrangler is there, cluster expansion and regression data. Let us execute this cell. Okay. So now in any cluster expansion, you need one structure that is the prim file of your system. Okay. What that prim file will contain? Let's execute this cell first. So this prim structure object, it is a structure object in the pymadgen.core.structure module, and the structure class represents crystal structures and contains information about lattice vectors of your system, atomic species and positions, and site properties, say occupancy, oxidation state, or magnetic moments. If we type this, if we print the type of this prim file here, so it gives the output of pymadgen.core.structure. Okay. So as we have seen here, this LNO prime is a structure object in the pymadgen.core.structure module. Okay. If we print this prim file here, let's see, this has the full formula of nickel lithium 0.5, nickel 1 and O2. So our prim file has lithium in it and this nickel and oxygen. So what is this prim? It is a disordered primitive structure of Li-NO2. Okay, and which defines the configurational space for the cluster expansion. If you want to model, say, AB alloy, which is FCC, let's say, so you will want your sites to be either occupied by A or occupied by B. Okay, so you will have that site active. Okay, suppose here if we see the first side, it is active, the allowed species are lithium positive and the vacancies. So this site can be occupied by either lithium positive or the vacancies, or the second one is active. The allowed species are nickel 3 plus or nickel 4 plus, and if we see other sites, those are inactive, those are not active, those are inactive actually. So only on those sites it is the only O2 minus which is allowed. Okay. If we can save the structure for the visualization as a CIF file here, and we can visualize it with any software, say Vesta. And if we see whether the prim is disordered or not, we can print that also, and it shows it is false. So it is not ordered, it is disordered actually, and which should be the case. Okay. If we see the reduced formula of the prim, so this gives Li 0.5, Ni1 O2. Okay. So now in any CE model we need some training data. Okay. The file LNO trainees and entries.json contains the training data set used to fit our cluster expansion model. So we have two files in our model. One is the prim file, other is the file which contains the training data here. This training data contains the DFT energies or the structures of our training data. Okay. So let us load this training data here, and we can type it, we can see the type of training data. So it is the list. Okay. If we see the type of first entry here, so it is the type is computed structured entry. Okay. If we see the length of entries, how many entries we have, so we have 31 data points here. We have 31 different configurations of nickel, lithium nickel oxide. If we take a look on the training structure here, let us print the first one or second one. So it has the this formula is Li1 Ni6 O12, and the energy is minus 194.276 electron volt. Okay. And we can have a look at the structure information of above data point here, and if we see this is the structure of this data point. Okay. This is the coordinates of all the atoms, lithium, nickel and oxygen. Okay. We can also check the composition of all 10 data points here. Okay. So this cell gives the composition of reduced formula of all the data points here. Okay. Now comes the important thing in the CE model we will construct, and that is called cluster subspace. What is cluster subspace? The cluster subspace represents all the orbits. And what is the orbit? It is a group of equivalent clusters. Okay, and that will be considered when fitting the cluster expansion. Okay, the main purpose of this cluster subspace is to compute the correlation functions. So we have this calculated DFT data which represents some maybe formation energies. We have this correlation matrix here, okay, of our system, and we have the effective interactions. Those are weights. Okay, as you can see here, we can clearly see that this CE model is actually a machine learning model, which is linear. Okay, and these are the weights, effective cluster interaction. These are weights of our model, and this is the feature matrix, or the correlation matrix in this case. Okay, so our job is to find this effective cluster interactions or the weights. So if we find these effective cluster interactions of our system, then we can use these effective cluster interactions to compute energy of any other configuration, any other, you can say 10 cross 10 cross 10 configuration. It's up to you. Okay. So what we provide? We provide prim structure represent the configurational space. Okay, so we give it a prim structure which represents our system, and then set up diameter cutoffs for each size of orbit we want to consider. So I told you we want to compute cluster interactions, point cluster, this pair cluster, triplet cluster. So we specify some kind of cutoff value to each to each cluster type. Say here, if we see here in this cell, we create a instance of cluster subspace class here. We have given subspace is equal to cluster subspace from the cutoffs. Okay, so we have given cutoffs to this 2 here means the cutoff for pair cluster. Okay, so the cutoff for pair cluster is 5 angstroms and triplet is 4.1 angstrom. Okay, and the basis we are using sinusoid basis. Okay, and then supercell size, to this supercell size specifies the method to determine supercell size when trying to match structures. If we execute this cell and print the subspace here, we can see here in this table degree represents, we have it is null cluster, and 1 is the point cluster, then again 1 is the point cluster, then we have 2 here, it is the pair cluster. Okay, and this has the diameter of 2.968 and multiplicity of 6. So it means we have 6 clusters of this type here with diameter of 2.9698 angstroms. So we can determine our correlation vector here. If we execute this cell here, say if we want to determine correlation vector for one structure, this one specifies LNO entries 1 here for first structure here. So this correlation vector for a structure with composition this is this. Okay, this is correlation vector here, gives 1.66 and so on. Okay, then comes the structure wrangler. So this class manages our training data. Okay, so it makes sure that all the supplied structures appropriately match the prim structure. And what it does, when we import our DFT data here, so it compares those DFT calculated configurations with the prim file and obtains some necessary information to correctly normalize target properties such as energy. Okay, okay, let's define the instance of this class here, and let's add the DFT data to this model. Okay, so we add all the training data points to the structure wrangler object. Okay, if we want to see how many structures which have matched, we can print that also here. So total structures that matched is 27 out of 31 structures. Okay, and if we want to see the shape of our feature matrix, okay, we can print that also. That's 27 into 11. Why 27? Because we have 27 data points here. Okay, we have 27 rows and 11 columns. Okay, we can print the shape of property vector also, 27, because we have 27 data points here. Now comes the training part of our CE model. Training a cluster expansion is one of the most crucial steps, right? So this is how you get the ECI values of your model. Okay, so if we see here, so we will use the linear regression to obtain our fitting parameters. Okay, we have defined estimator here. Linear regression fit intercept is called false. we can get the features from structural Wagner object here, and we can get the labels from structural Wagner object here, and this line this line is used to fit the model, and we can obtain the coefficients from this line. Let's execute this cell, and we can print the shape of our this coefficients. We can explore these coefficients also, and we can see it has the shape of 11. Okay, it is basically a column matrix. Okay, we can check the quality of the fit also. If we want to print the RMS value here. So the RMS value is 11.03 millielectron volt per prim. So if we kind of normalize with the number of atoms, it is very small. Okay, so typically in the cluster expansion, errors of say 1-2 millielectron volt per atom is fine. It's a very nice model then. So we have trained our model. We got the cluster interaction coefficients also. Okay, and the cluster expansion class can be used to predict the fitted property for new structure. Okay, as I told you, once we get the fitting parameters, we can get the energy of any structure then. And in this cell, we are doing that only. We will obtain energy of any other structure. Okay, if we see here, we randomly select a structure from training data. Okay, randomly. Then this is the predict. Okay, we predict the energy of that structure. Okay, and we can print that energy also, and we can print the fitted coefficients of that structure also. If we execute this cell here. Okay, so this one, the first value, this is the predicted energy by our model, and this is the DFT energy. Okay, if we print the expansion here, we can print the expansion. So you can see here this is the expansion we have. We have orbit ID, we have degree. Degree is the say we have 1, that is the point cluster, and we have 2 here, that is the pair cluster. We have the corresponding cluster diameter also. Okay, and each cluster will have its corresponding ECI value. If we see in this row ECI. Okay, if we want to see the quality of, we can visualize the quality of the fit here. We will plot basically the C predicted energies and the DFT calculated energies. Okay, let's plot this also. Okay, oh, you can see we have very nice plot here, and you can see that our model is very nice in predicting the energies of this configurations. Okay, and we can save our work like this. We save our work in this file celno.mson. Okay, let's save our work. So our whole work is saved in this file here, celno.mson. Oh, okay. Now that we have constructed our model and we have saved our work also, this model can now be used to construct to perform the Monte Carlo simulations. Okay. This is the end of this session. In the next session, we will use this model. This model we will use to perform the Monte Carlo simulations. See you in the next session.